In our last module, we have discussed the formulation of linear rank statistics, and we have seen some properties of linear rank statistics, and most importantly the distribution free property of a linear rank statistic. In this module, we shall give examples or the adoption of a linear rank statistic in two sample location and scale problems. We shall discuss Wilcoxon rank sum statistic and the associated test procedure. We shall discuss median test, and we shall discuss Terry-Hoeffding test for location problems and enumerate some properties. And further, for scale problems, we shall discuss Freund-Ansari test and close normal scores test and give the associated properties. Further, we shall extend the use of linear rank statistics to multi-sample problems through the Kruskal-Wallis procedure for one-way data. In this module, we start with two sample problems and the corresponding formulation of the linear rank statistics. In our previous module, we have defined a linear rank statistic. We have seen that the distribution of linear rank statistic is independent of any f under certain assumptions, and therefore we can use linear rank statistic to provide distribution free tests. In addition, linear rank statistic is asymptotically normal under fairly general conditions, and hence large sample tests based on the linear rank statistic can be constructed for various problems. So these are the advantages of using a linear rank statistic apart from the other advantages. So we start with two sample location problem. Suppose xi are n IID observations from some distribution fx, and yj are j are m independent observations from gx, and these two samples are independent, where f and g are unknown but known to be continuous. For a location problem, we assume gx as fx minus theta for some theta belonging to the real line, and then our objective is to test the null hypothesis that theta equal to 0 against the all possible alternatives, that is theta greater than 0 or theta less than 0 or theta not equal to 0. Suppose z is a combined set of observations, that is the set of observations comprising x1, x2, xn and y1, y2, ym, and we have in all capital N equal to small m plus small n observations in the combined sample. Let Ri be the rank of the ith observation in the combined set of observations, and we take Ci as 0 if I less than equal to small n and 1 if I greater than equal to n plus 1. So Ci can be interpreted as population indicators, that is Ci equal to 1 means we have representation from the second population, and Ci equal to 0 means we have no representation from the first population. Thus, the linear rank statistic reduces to L as summation I from small n plus 1 up to capital N a Ri, and clearly L is the sum of scores corresponding to the second sample observations. Now we shall discuss the choice of score function. For an appropriate choice of the score function, we need to know the behavior of ranks under a location alternative. First assume theta greater than 0. Then second sample observations are expected to be larger than the first sample observations. Naturally, ranks corresponding to the second sample observations are expected to be larger under theta greater than 0 than under theta equal to 0. Thus, if we take an increasing score function, then ARI are expected to be larger under theta greater than 0 than under theta equal to 0 for every I. Hence, L is expected to be larger under theta greater than 0 than under theta equal to 0. Again, if we assume theta less than 0, second sample observations are expected to be smaller than the first sample observations. Naturally, ranks corresponding to the second sample observations are expected to be smaller under theta less than 0 than under theta equal to 0. Thus, for an increasing score function, A or I are expected to be smaller under theta less than 0 than under theta equal to 0 for every I. Hence, L is expected to be smaller under theta less than 0 than under theta equal to 0. However, if theta not equal to 0, second sample observations are expected to be either smaller or larger than the first sample observations. Naturally, ranks corresponding to the second sample observations are expected to be either smaller or larger under theta not equal to 0 than under theta equal to 0. Thus, for an increasing score function, A or I are expected to be either smaller or larger under theta not equal to 0 than under theta equal to 0 for every I. Hence, L is expected to be either smaller or larger under theta not equal to 0 than under theta equal to 0. Critical region for the concerned testing problem. Thus, for increasing score function, we get right tail test based on L for the alternative theta greater than 0 and a left tail test based on L for theta less than 0. For the two-sided hypothesis, a two-tail test based on L would be appropriate. However, for the selected choice of Ci, the distribution of L under the null hypothesis is never symmetric. But depending on the choice of the score function, the distribution of L can be symmetric about the expected value of L under the null hypothesis. And hence, in such a case, the two-sided test reduces to a right tail test based on the absolute value of L minus expected value of L under H0. The distribution of L is clearly discrete under the null hypothesis, and hence exact size alpha tests will be in general randomized. So, we start with some examples. Suppose Ai equal to I, then L reduces to the sum of the second sample ranks. That is, L is nothing but summation I from small n plus 1 up to capital N of Ri, and this L is well known as the Wilcoxon rank sum statistic. It is already observed, derived that C bar is nothing but small m by capital N and summation I from 1 to n Ci minus C bar square as Mn divided by capital N. Again, for Wilcoxon score, we have A bar as capital N plus 1 by 2 and sigma square A as capital N square minus 1 by 12. Now, we can enumerate the properties of the Wilcoxon statistic. It is very easy to observe from the theory of linear rank statistic that under the null hypothesis, expected value of L under H0 is nothing but m times capital N plus 1 divided by 2, and variance of L under H0 comes out as Mn multiplied by capital N plus 1 divided by 12. The distribution of L is symmetric under the null hypothesis. For the assumed choice of Ci, we find that Ci plus C n minus I plus 1 is either 1 or 2. Thus, Ci plus C n minus I plus 1 is not a constant for all I, and hence we need to check the other condition. For the assumed choice of Ai, we find that Ai plus A n minus I plus 1 is nothing but capital N plus 1 for every I, and hence the symmetry of L under the null hypothesis follows from the results of linear rank statistic. Next, we shall compare Wilcoxon rank sum statistic and the already defined Mann-Whitney statistic. Actually, these two statistics have a very close relation between them. In fact, Wilcoxon statistic and Mann-Whitney statistic are linearly related. For a proof, we observe that rank of the Y ordered J in the combined sample is the number of X ordered I's less than Y ordered J plus rank of Y ordered J among Y observations. Now, rank of Y ordered J among Y observations is simply J, and when summing over J, the first quantity in the right hand side, that is the number of X ordered I's less than Y ordered J, is nothing but the Mann-Whitney U statistic. Again, the sum over J of the left hand side is Wilcoxon rank sum statistic L, and thus we get the relation L equal to U plus M multiplied by M plus 1 by 2. Thus, tests based on Wilcoxon statistic and Mann-Whitney statistic are equivalent, and hence they share similar properties. It is known that tests based on Mann-Whitney statistic are consistent. Due to equivalence, tests based on Wilcoxon rank sum statistic are also consistent. Further, the asymptotic normality of the Wilcoxon statistic also follow from that of Mann-Whitney statistic. Next, we shall discuss the large sample test corresponding to Wilcoxon statistic. It is easy to observe that Wilcoxon score vector satisfies no other condition, and hence the standardized variable L minus expected value of L whole thing divided by square root of variance of L under H naught is asymptotically standard normal. Thus, we can perform large sample tests based on N star, that is the standardized variable. In particular, a large sample test for theta equal to 0 against theta greater than 0 rejects the null hypothesis if L star exceeds tau alpha, where tau alpha is the upper alpha percentage points of a standard normal variable. Similarly, the large sample tests for the remaining alternatives can also be constructed. Next, we shall discuss median score and the associated statistic. Suppose AI is the indicator of I greater than capital N plus 1 by 2. That is, we have AI equal to 1 if I exceeds capital N plus 1 by 2 and 0 otherwise. Now, capital N plus 1 by 2 may not be an integer, so we have used some box function or the greatest integer contained in N plus 1 by 2. Then, with this score, L reduces to summation I from small n plus 1 to capital N indicator capital Ri greater than box n plus 1 by 2. Thus, L is the number of the second sample ranks exceeding n plus 1 by 2, and L is well known as Moore's median test statistic. For median score, we can find A bar and sigma square A, and hence the variance of the median score statistic can also be obtained. Now, it is interesting to observe that with the definition of median score statistic, we can find the null distribution of such a statistic. From the first principle, it follows that the probability of capital L equal to small l under the null hypothesis is nothing but the number of choices of R n plus 1 up to R capital N out of 1 to capital N such that capital L equal to small l whole thing divided by capital N choose n. Thus, we find the null distribution of L as similar to hypergeometric. Actually, it is hypergeometric. Now, if we want to study the properties of such a statistic, we find that from the property of linear and statistics, the expected value of L can be obtained as m times 1 minus box n plus 1 by 2 divided by n, and in a similar way variance of L can be obtained, and for the median score we find that ai plus a n minus I plus 1 equal to 1 for all I, and hence the symmetry of L under the null hypothesis follows from the results of linear rank statistic. As we have discussed in case of Wilcoxon rank sum test, a large sample test corresponding to the median score statistic can also be found and can also be constructed, and some large sample tests can also be constructed. We shall discuss linear rank statistics in scale problems. Suppose we have IID observations xi from some distribution f x minus mu1 by sigma 1 I from 1 to small n independently of yj, which are IID observations or MIID observations from a population f x minus mu2 by sigma 2, where f is unknown but known to be continuous. If sigma 1 equal to sigma 2 but mu1 not equal to mu2, the distribution of rank vector is not uniform. Hence, no exactly distribution free statistic or test is possible using n. However, if sigma 1 equal to sigma 2 and mu1 not equal to mu2 but mu1 mu2 is known, exactly distribution free test can be derived using L. So, in order to get distribution free tests using L, we assume that two distributions differ only in location. That is, we assume xi are n IID observations from fx and yj are m IID observations from f x by sigma, where sigma is a scale parameter and is positive. Then our objective is to test sigma equal to 1 against all alternatives. As earlier, we take the linear rank statistic as summation I from n plus 1 to capital N ARI. That is, L becomes the sum of scores corresponding to the second sample observations. Now, we shall discuss the choice of score function. Suppose observations are positive with probability 1, then sigma greater than 1 implies and implied by fx greater than or equal to fx by sigma for all x, which again implies and implied by y is stochastically larger than x. And similarly, if sigma less than 1, then this in turn implies and also implied by that y is stochastically smaller than x. Thus, tests for stochastic alternatives, as for example Mann-Whitney test, are all applicable for testing sigma equal to 1 against all alternatives. Now we shall discuss choice of score function. Now assume observations on the whole real line together with symmetry, that is fx plus f of minus x equal to 1 for all x. Then sigma greater than 1 implies that the second sample observations are expected to have lower concentration than the first sample observations. Naturally, observations corresponding to the second sample observations are expected to be either too large or too small. Thus, second sample ranks are expected to be either too smaller or too larger under sigma greater than 1 than under sigma equal to 1. Thus, if we take a symmetric U-shaped score function, then ARI are expected to be larger under sigma greater than 1 than under sigma equal to 1 for every I. Hence, L is expected to be larger under sigma greater than 1 than under sigma equal to 1, and hence a right tail test is suggested. Similarly, L is expected to be smaller under sigma less than 1 than under sigma equal to 1, and hence a left tail test is suggested for when all the alternative is sigma less than 1. And similarly, we can get a two tail test based on the absolute value of L minus expected value of L under H naught for testing the alternative sigma not equal to 1. Further, one can also use a bell-shaped symmetric score function, but in such a case the rejection regions will be reversed. However, the distribution of L is discrete under the null hypothesis, and hence exact size alpha tests will be in general randomized. Now, as in the median statistic or median test statistic, we can find the null distribution of such a L corresponding to quartile score, that is when AI is 1 minus indicator box n by 4 less than I less than box 3n by 4. However, such a null distribution is not symmetric but is asymptotically normal, and hence large sample tests can be performed as usual. So further, we can use a number of scores for the scale problems to get the corresponding tests. We can use mood score, which is I minus n plus 1 by 2 whole square. We can use Ansari-Bradley score, which is the modulus of I minus n plus 1 by 2, or we can use Cloge normal score, which is phi inverse I by n plus 1 whole square. And all these tests can be carried out in large samples. Next, we turn our attention to multiple sample location problems. Suppose xij are independent as fx minus theta I for j running from 1 to ni and I from 1 to k, where f is unknown but known to be continuous. Then our objective is to test the null hypothesis that theta 1, theta 2, theta k are all equal against all alternatives. Thus, we get a non-parametric model of one-way classified data. Intuitively, if Ri is the rank of the ith observation in the combined sample of capital N observations, then the distribution of ranks Ri, I from 1 to capital N, is uniform under the null hypothesis. If the null hypothesis is true, then the total sum of ranks, that is n into n plus 1 by 2, is expected to be divided proportionally among the k samples. That is, under H naught, the sum of ranks for the ith sample is expected to be ni multiplied by capital N plus 1 by 2. If the sum of the observed ranks assigned to the ith sample is denoted by Ri naught, a reasonable test statistic could be based on the deviations between these observed and expected rank sums. Thus, Sums of these squared deviations is a reasonable statistic. In particular, we suggest S as summation I from 1 to k Ri naught minus small n I times capital N plus 1 by 2 whole square to measure the deviation from the null hypothesis. Naturally, a large value of S indicates deviation from the null, and hence we reject the null hypothesis if S is too large. Now we discuss Kruskal-Wallis test. It is quite obvious that S provides a distribution free test of the null hypothesis. However, a more useful test criterion is a weighted sum of squares of deviations, where the sample size reciprocals are used as the weights. Following the above argument, Kruskal and Wallis define the statistic. The definition is given in the slide, and as before, using this H, we reject the null hypothesis if H is too large. However, tests based on S and H are equivalent when the number of observations from each sample are the same. As earlier, one can perform a large sample test based on H, and it can be shown that under certain conditions the large sample distribution of H under the null hypothesis is chi-square with k minus 1 degrees of freedom. Therefore, an asymptotically psi alpha test rejects the null hypothesis if the observed value of H exceeds chi-square, the upper alpha percentage point of a chi-square k minus 1 variable. Thus, we have seen how linear rank statistics can be used in location and scale problems, and we have seen some properties and discussed some properties. For the discussion, we have assumed that the two populations differ only in location or in scale, but in practice two distributions can differ both in location and scale, and we can develop distribution free test for such a model. However, such discussion is beyond our scope, except just mentioning.